Alright, this is the summary of the back of the solar panel label. They're going to give you the short circuit current, the open circuit voltage, the maximum power point current, maximum power point voltage, and the max power point under STC conditions, which is 1000 watts per meter squared, 25 degrees C, and an atmospheric mass rate of 1.5. Harkening back to our diode model, this is the equation for the diode part of that model. The I photon is the solar photonic energy, light, watts per meter squared number. And this is the losses in the series resistance up here. Okay. The Q is a standard engineering value, is electron charge. K is the Boltzmann's constant. T is temperature in degrees Kelvin. Okay. I naught is a current. It's probably on the order of 1 to 10 times 10 to the minus ninth in magnitude. Very, very small, but becomes dominant once the voltage in this parentheses gets large enough. Okay, now there's a fundamental problem with this equation. I, as the output, is dependent on I as the input. What this means is that this equation cannot be solved directly. There's no way to factor it and make it easy to solve or anything else like that. And going back up to our current versus voltage curve, ISC is the short circuit current, is over here. Now, RSH from this circuit diagram can be extracted by the slope close to the short circuit. RS can be extracted by the slope close to the open circuit voltage. And this is the standard IV curve of a solar cell or solar panel. Okay. With this back panel label, we get 3 points. We can draw a straight line from the short circuit to the max power point, and from the max power point to the VOC as a first crude approximation. It's going to make the resistance for the shunt to be lower than what it actually is, and the resistance for RS to be higher than what it is. Alright, this curve, the actual curve by this equation, should be very close to a straight line of ISC and a straight line to VOC. Okay, the max power point is down here. Since this is all this data is at standard test condition, it does not represent the performance of your solar panel. It represents the performance of your solar panel tested in the laboratory or the manufacturing floor. A solar panel, a nominal operating temperature, is going to be 20 to 30 degrees higher than the test condition temperature here. And temperature is here, and because temperature is here, it also falls over here indirectly because of this part of the equation. Okay. If you have a sophisticated computer simulation and you can iterate it 2 or 3 times, you can pick nominal values and get it to solve this equation very nicely. Alright? Joe Blow, me, and you are not going to be able to do that. Now, the one interesting thing I didn't mention on the last video is that ISC, the short circuit current, has a very small temperature dependency. The other thing is, this part of the equation for the range that human beings live at can be approximated with a straight line, and we'll substitute that in the next video as a straight line. The fact that the ISC is not temperature dependent, and we know that it's a certain value at 1,000 watts per meter squared, we can estimate the solar radiation hitting the panel just by measuring ISC.